Okay, so last section we're going to look at for this week is 11-2. We'll split it into 2 days. Day 1 is going to be on what we call a finite series. That means adding up numbers that have an end. So you're not adding up forever. You stop somewhere. And then tomorrow we're going to look at adding up an infinite amount of numbers. It might seem kind of weird. How can you add up an infinite amount of numbers? Well, you can, depending on the numbers you're adding up. Depends. All right, so in the last section, we used this notation to represent a sequence. We used the lowercase letter to represent the name of the sequence, and then the little subscript that represents the position. So a sub 1 would be the first number in sequence A. A sub 2, second number. All right, let's think about this sequence. And let's write out the first, maybe 4 or 5 terms. Okay, so I'm going to do the position and then the term in that position. Okay, so the first one, we're going to plug in 1. Okay, what's 2 times 1? 2. And then minus 1? 1. Let's just leave it as 1 to the second power. Okay, we can simplify that if we want later on. But let's leave it like that, and I think you'll see a pattern. Okay, so 1 squared. Now let's plug in 2. What's 2 times 2?
4.
4 minus 1?
3.
So that's 3 squared. And then when you plug in 3, 2 times 3 is 6. And then minus 1?
5.
5 squared. Any guess on what the next one is?
7.
7 squared. If you write it like that, it makes the pattern easy to see. It's odd numbers squared, starting with 1. If you do these out, makes it a little harder to see. Like this would be 1. This would be 9, 25, and 49. If you did them all. Okay. Any question on how we got those terms? Okay. So now, instead of just looking at these terms, we're going to look at adding them up. So we're going to add them up. And depending on how many you want to add up, we're going to use a notation to do that. When we use a capital S and a small n, that's going to mean the sum of the first n terms. Okay, so if I did something like this, S sub 3, that would mean take the first 3 terms and add them together. Okay, so let's try it out. S sub 1 means to add up, it's kind of weird, but you just add up the first 1 terms. What's the first term in that sequence? 1 squared, it's just 1. So if you add that up, and that's the only thing you're adding up, what do you get?
What?
1. Yep. You get 1 squared, or you get 1. Now S sub 2 means to add the first 2 terms together. Right? What's the first term?
1 squared.
And what's the second term?
3 squared.
1 squared plus 3 squared. Yep. And that's the sum of the first 2. Let's do the sum of the first 3.
We have to get 10.
1 plus 9.
Oh, alright.
Okay. Can somebody list off the first 3 terms?
1 squared, 3 squared, 5 squared.
1 squared, 3 squared, 5 squared. And that's 25 plus 10. It's 35. And then, in general, if you wanted to add up the first n terms, well, you do the first one, you do the second one, you do the third one, dot, dot, dot. You keep going till you get all the way to the nth term. whatever that happens to be. 10th term, 50th term, 200th term. We don't know. So any question on the idea of what that notation means? Now, look at the numbers in red. 1, 10, 35. 1, 10, 35. That's a new pattern of numbers. That's the pattern of numbers that you get when you add up the first n terms. So this is when you add up the first one, the first two, and then the first three. Now, if we can predict that pattern, then we could add up as many as we want. Right? The key is, can we somehow predict what would come next after 35? And that's what I'm going to show you. And then if you can predict that one, you can predict anything you want. So if you want to add up, let's say you want s sub 200. Well, then you're not going to have to sit here and do 1 squared plus 3 squared all the way to 200. Right? That's going to take a while. So we want to find a shortcut. So we'll see if we can. So each one of those things that we wrote down, let me go back, put it up. S1, S2, S3, Sn. Those are what we call a finite series. It means you added up a bunch of numbers, but they didn't go on forever. There was a limit. S3, you added up the first 3. S2, you only added up the first 2. S sub n, even though it's unknown where you're still stopping somewhere. Maybe n is 1,000,000. You're going to add up the first 1,000,000. That's still what we call finite. There's an n. Now, if you do something like this, s sub infinity, well, that's not finite. That means now you're adding up an infinite amount of numbers. Okay, so that we'll save for tomorrow. Okay, so finite means that you only have a certain number of things you're adding up. So any question on what the idea of finite means? Even if it's a lot of things, even if it's millions or billions of things you're adding up, it's still finite because it stops somewhere. All right. So I kind of already showed you this, but let's think about this sequence again. So let's suppose now we don't have a specific sequence, but just any sequence, okay? A sub n, whatever it happens to be. Well, the first partial sum is just when you add up the first term. Okay, so whatever the first term is, that would be the first partial sum. The second partial sum is when you add up the first 2 terms. How about s sub 3? What do you think that would be?
First 3 terms.
The first 3 terms. The only difference between what I'm writing here and what I did over here is on the left, that's a specific example with actual numbers. On the right, that's more general. I don't know what the first term, the second term, and the third term are. Could be anything. Depends on the formula. But that's the idea. And then you can go all the way to the nth term. But remember, n is a number. Maybe it's s sub 100, maybe it's s sub 10, who knows? Okay, but it stops somewhere. So that's the first partial sum, second partial sum, third partial sum, and this would be called the nth partial sum. And the reason they're called partial is because you're not adding up every single number that there is. You're only adding up some of the numbers. Like just the first 2 or just the first 3. Depends how many you're adding up. So writing this out can be kind of tedious. Like, let's say I wanted you to represent writing out every single number from 1 to 1,000. Well, and adding up every single number from 1 to 1,000. So you could write down 1 plus 2 plus 3, and I don't want you to use dot, dot, dot. I want you to represent everything. Well, that's going to take a while. So there's a notation that we can use that represents adding up every single number from 1 to 1,000. And it's a very short, kind of compact way to do it. And it's called sigma notation. To use this notation to add up a bunch of numbers, you need to know 3 things. 1, where are you starting? 2, where are you stopping? And 3, what's the formula that's generating the numbers you're adding up? And there's 3 spots that we put those things. Okay, and that's what it looks like.
What did you say that we did? The formula, the first term, and the term that we're stopping at?
Yeah, to use this notation, you need to know where you're going to start, where you're going to stop, and then you need the formula that's generating the numbers you're adding up. All right, so let's say that we want to represent adding up a bunch of numbers. The first, the second, the third, the fourth, the fifth, the sixth, maybe all the way up to the 100th term. That's the notation that we can use. So let me show you an example with something kind of concrete so you can see it. Let's say I wanted to represent adding up the first 5 numbers in this pattern. A sub n equals n plus 2. Well, let's write them down. Position and the term. Okay. What would be the first term in that sequence?
3.
3. And the second term?
5. No, it's 4.
4. Third term?
5.
5. And the fourth term?
6.
Ah, good enough. So let's just add up the first 4. So if you want to represent adding up 3 plus 4 plus 5 plus 6, this is how you do it. First thing is you put down your formula on the right-hand side. So we put down we normally use the letter N. You're probably going to see the letter K used in this section. It doesn't really matter what letter you use, but I'm just going to use K because that's what you're going to see more in this section. So put down your formula on the right-hand side. At the bottom, tell me where you want K to start. So what's the first number you want to plug into that formula? If you want to start at position 1, then you let it be 1. And then at the top, you put where you want it to stop. So this notation right here represents doing 3 plus 4 plus 5 plus 6. And the way you figure that out is you take the number at the bottom, which is k equals 1, you plug it in for k, and then you write down that number. Then you put a plus sign, and then you go up 1 at a time. Then you plug in 2 for k. 2 plus 2 is 4. Write down that number. Then put another plus sign. And you keep letting this number go up 1 at a time until you get to 4, and that's where you stop. And that's called sigma notation.
So the top is stopping, the bottom is where you start.
Yeah.
And then the one on the right is your formula.
And that's your formula that you're plugging all the numbers between that number and that number in. Yep. So the way that you would pronounce what's in that red box right there is you pronounce that capital sigma as the word the sum. So it's the sum from, and in this one it would be 1 to 4. In this one you would say from 1 to n. We don't know what n is, but it would stop somewhere. So the sum from 1 to n of, and then you read your formula, a sub k. Okay. In the one that's circled on the right, I would say the sum from 1 to 4 of k plus 2. So it tells me where to start, stop, and the formula to plug into. Okay, the k is what we call the index. It's the thing that keeps track of where you start. Okay, that's called your index. Most of the time, the index starts at 1. It could start at a different number, but most of the time it just starts at 1. Does everyone have the line that says the sum from k equals 1 to n?
I'll give you a sec.
Okay, I want to show you something. Let me write this down. The sum from k equals 0 to 3 of k plus 3. So watch what happens here. What's the first number they want me to plug in for k?
0.
0. And what's the formula I'm plugging it into?
K plus 3.
K plus 3. So let's plug in 0. What's 0 plus 3?
3.
3. Plus, what's the next number I plug in for k?
2. 2. 3. 1. 0. 8. 7, 6, 5, 4, 3, 2, 1.
So what's the next number we plug in for k?
4.
Why 4?
Question? 3. I mean 3.
So this number is supposed to go up 1 at a time.
So 1.
1. So plug in 1. What's 1 plus 3?
4.
4. And then what's the next number we plug in for k?
2.
2. 2 plus 3?
5.
And the next number?
3.
3. And 3 plus 3?
6.
6. Is there a next number?
Nope.
No, because we just hit 3. We hit the stop. What do you notice about this one compared to the one above it?
It's exactly the same sequence.
Yeah, it ends up being exactly the same answer. Do they look exactly the same?
No.
No. The formula's a little different. Where you start's a little different, and where you stop's a little different. But everything was adjusted just the way it needed to be so that if you do it out, it comes out the same. Okay. So the point here is there's really an infinite number of ways you could write 3 plus 4 plus 5 plus 6. You could start at 0, you could start at 1, you could start at 2. You can start at any number you want. You just have to keep adjusting your formula to make sure it still gives you 3 plus 4 plus 5 plus 6. Okay, but I would say 1 is the most common place to start. Any question on that idea? Okay, and the fancy name of what I just did right here, what's k called? K is the what?
Index.
It's the index. That's called re-indexing. It's when you change where it starts, but then you adjust the formula so you still get the same answer you had before. You've changed the index. All right, let's look at this one. So let's write out what this would mean. Okay, what number are we going to start at?
1.
1. And where are we going to stop?
5.
We're going to stop at 5. And the formula we're going to plug into?
2k plus 3.
2k plus 3. So you plug in every number from 1 to 5, going up 1 at a time. Okay, so we plug in 1. What's 2 times 1 plus 3? 5. And now if you plug in 2, what's 2 times 2 plus 3?
7.
7. And if you plug in 3, 2 times 3 plus 3?
9.
That's 9. 2 times 4 plus 3?
12.
11.
11. And 2 times 5 plus 3? 13. That's it.
That's it.
Yep. So this is called sigma notation. That's called expanded notation. I think I write that down on the next page. When we write that, sigma, yeah, I'm going to write that down. Okay, but on the left, sigma notation. On the right, you've expanded it out. And you could add up all those and write down what it is. All right, so when you write something that looks like this, that is called sigma notation. And the reason it's called that is because that's the Greek letter for sigma. It's a capital sigma.
What's lowercase sigma?
The lowercase sigma, I'm trying to remember. It might be the little circle with the line on it. Let me just. Okay, so the top one is sigma. And then when you actually write it all out, plug in the numbers starting at the index, stopping at the top number. That's called expanded notation. So you might see directions on a test that say expand the following, and then they give you a problem. Like this one. It says expand, means to do that. Any question on the difference between sigma and expanded? Okay. Now, I think we just, we could do this one. Now, where are they having me stop here? At n. We don't know where n is. So what I usually do then is I do like the first 3, and then I put ... and then I do the last one, which in this case would be plugging in n. All right, so let's do the first one. What's 2 times 1?
2.
Plus 3?
5.
All right, so that's 5 squared. Well, you could do 25, but it's 5 squared. Plus, what's 2 times 2?
4.
Plus 3?
7.
So 7 squared. Now let's do one more. 2 times 3?
6.
Plus 3?
9.
9 squared. Okay, so I get the idea. 5 squared, 7 squared, 9 squared, plus, there might be a bunch more. Should be 3 dots. And then what's the last thing you plug in for k? N. So it's going to be 2n plus 3 squared. So that's how you expand something when you don't have a number for the last one. Just show the first 3. That gives an idea of what the pattern is. And then say, okay, here would be the last one. How many are in the ... We don't know. Depends how high n is. Any question on expanding that one? Okay. All right, so let's look at a few properties of summations. Okay, these properties are basically going to allow you to take something that has 2 separate summations and combine them into one. As long as they start at the same index and they stop at the same index, combining them into one is very straightforward. You basically just look at this, you look at that, and you end up combining like terms. So you end up writing one of these sigma symbols, and then you combine your like terms. Okay, but I'll write down the property so you can see it. So here's our first property. If you're adding together 2 sigmas, and they start at the same spot, they stop at the same spot. If they don't, then you can't do this. They have to start and stop at the same spot. And you want to combine them into one sigma, like the left side. just take A sub k, which is the formula for the first sigma, take B sub k, which is the formula for the second sigma, and add the two formulas together. Basically combine like terms. All right, so when we do this on the problem we're going to do in a second, think of this as A sub k. Think of that as B sub k. So you're going to add them together, and you're just going to have one sigma in front when you're done, instead of two. Let's try it with this one. So put down your sigma. Okay, where does it start? Starts at 1. Where does it stop? N. And now I want to know the new formula in that box. Instead of doing them separate, I'm going to combine it into one step. So take what's in the first box and add it to what's in the second box. And that's how you can combine it. Okay, let's start with the squared terms. We have 5k squared plus k squared. What would that give me? 6k squared. We don't have any k's here, and we have a negative 2k here. So what would come next? Minus 2k. And then we have a minus 4 plus 7.
Plus 3.
So that's going to give you a plus 3. And that's it. That's your answer right there. So that you are allowed to do that. You can take two sigmas and combine them into one, just like that. And you'd get exactly the same answer. Like if you had a formula and you did out the first one and then you did out the second one and added it, or you just did this formula. You get the same thing, but the second one's a little bit shorter because it's all combined together. Any question on that? Now, if that works with addition, you can also do the same thing with subtraction. If you had to subtract two different sigmas, you can combine them into one. But when you combine them, don't add the two, subtract the two. So addition and subtraction pretty much work exactly the same. You just want to be careful when you subtract, because if this was a minus sign right here, this minus gets applied to everything. So what property does that make you kind of think of? It's like distributive, right? If you're subtracting something, like if you're subtracting this formula, you're subtracting 7, you're subtracting negative 2k, and you're subtracting the k squared. You're subtracting the whole thing from the first formula. Okay, so that's our second rule for combining together. And this is our third rule. And maybe I'll show you this one with an example. Let's say we have a simple sequence. 2, 4, 6, 8. And C is a constant. Let's say I want to triple that sequence. Let's do it the way on the left, then let's do it the way on the right, and see what happens. Let's find that. This means to multiply your sequence by some constant. Right? In my case, it's going to be 3. So if you multiply this entire sequence by 3, what do all the terms become? 6, 12, 18, 24, 24. That's 3 times my sequence. Now, let's add up, in this case, all the numbers from 1 up to the 4th term, because I only have 4 terms. So let's add them all up. So 6 plus 12 is 18 plus 24. Well, what's 6 plus 12? 18. What's 18 plus 18?
36.
36. And what's 36 plus 24? 60. So that's doing it the way on the left. You tripled all the numbers in the sequence first and then added them up. Okay, now let's do it the way on the right. The way on the right says add up all the numbers first and then triple it at the end. All right, so let's take our sequence. Let's add up all the numbers first. Okay, what's 2 plus 4? 6 plus 6?
12.
And 12 plus 8?
20.
So we get 20 for this. Well, actually, we get 20 for this. We added up all the numbers in the sequence. Now, take the answer we just got and triple it. So what do we get if we triple 20? 60. You get exactly the same thing we did up above. So it's just two different ways to add up numbers in a sequence if you want to multiply them all by something. You can multiply them all first and add them up, or add them up the way they are and multiply at the end. I think this way is easier because you're adding up a smaller numbers, and then you're just tripling it at the end. Right, so the point is, anytime you have a number here, you can move it in the front. Those are the basic properties that we can use with sigmas. Any question on those properties? All right, let's try one more of those. Let's do something like, what example was that? That was 2. We'll call that 2a. Let's do 2b. Let's take the sum from k equals 1 to n of, let's do 2k squared plus 3 minus the sum from k equals 1 to n of 3k squared minus 5. And I want to combine that into a single sigma. Okay. Where does my sigma start? Yep, it always stays the same place it started originally. It starts at 1, and where does it stop? N. And now we just need to put the formula that combines the two together. So we have a 2k squared minus 3k squared.
-1, so -k squared.
Yep, negative k squared. And then a 3 minus 5. 8. Yep. That's how you can combine those two sigmas into one. And that would be a lot less steps if you really wanted to do what you have up above. The bottom way is a shorter way to do it. Hey, any question on that? So sigma notation gives us at least gives us a short way of saying what you want to do. It doesn't actually give you a short way of doing it. Right? If I want to add up, let's say every number, or actually, let me write that. Tell me, what does that represent?
It stops at 100 and starts at 1.
Okay. And what's my formula? And I should have just made it a K. Sorry.
No.
So, what am I really doing there?
You're just gonna write the numbers out.
What numbers?
From 1 to
Every number 1 through 100.
And then do what with them?
Add them all.
Add them all up. This represents adding up every number from 1 through 100. It's a short way of writing what you want to do, but it doesn't actually give you a quick way of figuring out the answer. That's what sigma notation doesn't. If you're clever, you could kind of figure out what the answer is. Because if you went like this, and you have a bunch more terms, let's see, at the end you would have, 100, 99, 98, 97, 96. Okay, you want to add all those up. Well, there is a way you could kind of figure it out. Does anybody know a clever way to add up every number from 1 to 100? Tried to give you kind of a hint there.
Pair.
You want to pair them up. Yeah, how could you pair, what could you pair this one with?
99.
Pair with 100.
I would pair it with 100, yeah. And what do those add up to?
101.
So you get a 101. And then pair 2 with what?
199.
A 99, and what do you get?
101.
Another 101. So it's just a matter of how many pairs of 101s do you have, and you would get, I think it would be 50 pairs. So if you take 50 pairs of 101, that's what they add up to. Now that's just kind of a trick to do that one. But how do you do something like that in general? You know, that's what I'm going to show you. So again, sigma notation, it's a compact way of writing something down, but it doesn't actually speed up any calculations. You still have to do it all out. So if you wanted to add up every number from 1 to 10, you could kind of use the same trick I just gave you. You have a 1 and a 10, that's an 11. 2 and a 9, that's an 11. 3 and an 8, 7, and so on. And figure out how many pairs of 11 do you have. Or, if you know this formula, that's what every number from 1 to 10 adds up to. 1 plus 2 plus 3 all the way up to plus 10. It adds up to 55. And there's a way I did that very fast without actually thinking about, okay, 10 plus 9 is 19, plus 8 is 27 or whatever. I figured it out using a shortcut. And I'm going to show you what that shortcut is. Okay, without the shortcut, you still got to add everything up by hand. Now, the formula that I'm going to show you for some of these shortcuts, we're not going to go through and prove where the formula comes from. We'll try it, and I'll show you it works. We're not actually going to go through proving it from scratch. Okay, the first one is very easy. I'll show you that one first. What if I wanted to add up, let's say from k equals 1 to 10 of 3. That's my formula. My formula is 3. Let's do it. So you're supposed to start with 1, plug it into your formula where you see the k, and then write the answer down. So we're going to take 1, and we're going to plug it in for k in what I just circled. Is there a spot for k?
No.
No. So if you plug in 1 for k, what do you get?
3.
You get 3. What if you plug in 2?
3.
You get 3. How many times are we going to get 3? We're going to get it 10 times. So we just end up getting 3 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what does that give you?
30.
30. So do you see a shortcut? Instead of plugging in each number one at a time and then writing it out, do you see a shortcut here?
Multiply by 3 and 10.
Yeah, you just multiply those two numbers together, and it tells you the answer. What's that?
You have to divide by the bottom.
Nope. Nope. You just add up all. You just do 3 times 10, and that's the answer.
Because there's no K.
Yep. Because there's no K in that formula. So let me show you that one. Okay, so here's the first formula. If you want to add up a number n times, right? C represents a constant. Let me put the example back that we just had. In our example, n was 10 and c was 3. If you have something like this, the answer is just going to be the product of those two numbers, c times n. And that's only because there's no k on the right-hand side. Now that is not what I used to figure this out, because that has a k on the right-hand side. But it's k to what power?
1.
Yeah, it's k to the first power. So anytime you have a k to the first power, and you want to add up all the numbers from 1 to whatever, 1 to 10, 1 to 100, that's the formula that will add them all up. So let's see how I did this one. You can check it. If you add up 1 plus 2 plus 3 plus 4 plus 5, 6, 7, 8, 9, and 10, you do get 55. That is the answer. So let's apply this formula to this problem. How many numbers are they having you add up in this case?
10 numbers.
10 numbers. N is the top number. So we're adding up 10 numbers. That's why I put 10 for n. And then next to it, you put 10 plus 1, 11. And then you divide by 2. Let's try it from 1 to 5, just to show you it works.
So you said that's when only k is to the first power.
Only when k is to the first power. Yeah. K is to the second, third power, it gets more complicated. We're only going to look at those two formulas, though. That's all we do. Okay. What do you get if you add up the first 5 numbers? So that's doing this. Oh, I keep doing that. And we're stopping at 5. You get 15. Okay, now, what was n in this case? N was 5. What's n plus 1?
6.
6. And divide by 2. What's 5 times 6? 30.
15.
And what's 30 divided by 2?
15.
15, what they added up to. So now, if you wanted to add up, let's say every number, k equals 1, 2, 20. What's n in this case? 20, that's what you're stopping at, times what's 20 plus 1?
21.
21, and divide by 2. What's 20 divided by 2? 10. And what's 10 times 21?
210.
210. So if you want to manually add up 1 plus 2 plus 3 all the way up to 20, it's going to add up to 210. So it gives you a quick way to add them all up. And again, it only works if the formula on the right-hand side is a k. There is a formula for k squared and k cubed, but we're not gonna need it. Thank you. Okay, so these are the two that you need to know. So what these formulas basically do is they get rid of the sigma. Okay, there's nothing wrong with sigma. It's a nice way to write things, but it doesn't actually help you to do anything. It's just a short way of saying what you want to do. This is a short way of actually doing it. Okay? Gives you a formula that automatically adds them all up for you. All right, so let's try an example. So let's simplify this sigma. So when I'm done, I don't want to have a sigma left in this problem. Bring up the other page that we had. There we go. So we're going to use these. What we want to try to do is, instead of having it all combined together, let's separate it. Okay? Separate it into multiple sigmas. Okay, that's how we simplify it. I think I deleted a page that I'm going to need. Is it coming back? that's where it was. All right, so the first thing I want to do is separate this into two different sigmas, right where that plus sign is. So I'm going to do a plus. I'm going to have a sigma here and a sigma here. Where do both of them start? Yep, they both start at 1. Where do both of them stop?
N.
Both stop at n. What's going to be the formula for the first sigma?
Negative 2K.
Negative 2k. And the formula for the second sigma?
3.
3. Now, look at this one. Does that look like either one of these?
It's like number 1.
It is. It's number 1. So we can simplify that to 3n. That whole thing just turns into a 3n. I won't do it yet, but that's what I'm going to do in the next step. Now, does this one look this one? Does it look kind of like one of these?
Yeah.
Kind of looks like 2, but there's a number in front of the k. Now, earlier we said that if you have a number, where was it? Oh, go back another page. Formula 3. If you have a number in front and you don't want it there in front of your formula, what can you do with that number? We can put it in front of the whole thing. Okay, let's do that and watch what happens. Okay, what number goes in front?
-2.
So negative 2. And then we'd have k equals 1 to n of k. That's exactly what that is. So we can change that sigma now to something. And the other one, k equals 1 to n of 3. What did we say this one on the end is going to be?
3n.
3n. Yep. It fits this pattern of number 1. So it's just the product of those two things. But we had to break it down so we could see that it was that. So this is 3n. And now look at this part right here. The sum from k equals 1 to n of k. That's exactly what rule. From the other page.
Second one.
Yeah, that's exactly this formula right here. K equals 1 to n of k. So what can I substitute for what's in this box?
N
Yep.
times n plus 1 divided by 2.
N times n plus 1 divided by 2. So the point is it gives me a formula to substitute in for the sigma. Don't forget about the negative 2. That's still in front. Now, you have a 2 in the top and a 2 in the bottom. So what happens there? 2 cancels. Now you have negative n times n plus 1 plus 3n. And now you just combine like terms. What can you do with this negative n that's in front? Yep, you have to distribute it. What's negative n times positive n?
Negative n. Negative n squared.
Negative n squared.
Oh, yes, sorry.
And what's negative n times positive 1?
Negative n.
Negative n plus 3n. And what's negative n plus 3n?
Minus 2n.
Yeah, 2n. So what you're doing is you're substituting for sigma, and then you're getting a formula that would be very easy to work with. Now, if you wanted me to add up every number from 1 to 500, instead of trying to plug in 1, and then 2, and then 3, and then 4, all the way up to 500, and then adding them all up, all I have to do now is plug in the number 500, square it, and then add 2 times 500. It's a much faster way to add up those 500 numbers. Question on that? Let's try one more like that, and I think that's where we'll stop. So we won't do anything else for today. Let's do the sum from k equals 1 to n of, let's do 4k plus the sum from k equals 1 to n of 5. Okay, the last one already fits one of the patterns. Can anyone tell me what that turns into? Turns into 5n. You're just adding up the number 5 n times. So it's 5n. Now the first one we have to fix a little bit. What do I have to do to fix that so it looks like the one on the left?
The 4 in the front.
Yep, the 4 in front. So it's 4 times the sum of k equals 1 to n of k plus 5n. What does this part turn into based on our formula? Yep. So what is that going to be? 4 times n plus 1 divided by 2 plus, what do I still have right here? 5n. Yep. Anything I can reduce in this first fraction?
4.
Yep.
2.
4 goes in 2 times. Now I've got 2n times n plus 1 plus 5n. What's 2n times n?
2n squared
2n squared
plus 2n
plus 2n plus 5n. All right. And what will be my final answer?
2n squared plus 7n.
2n squared plus 7. Question on that?
No.
Okay, so I would definitely write down these two formulas, and every problem you do like this, it's got to end up like looking like one of those two things every time. Okay, I'm not going to give you one that has a k squared in it or a k cubed. Okay, it'll just be a k.
Can you actually hold up that k cubed thing so I can just copy it out for future reference?
The k squared and the k cubed, yeah, I can, but you don't need to know anything below that for this.
That's fine. Don't need to know, but nice to know.
All right, so I gotta adjust the homework a little bit. Okay, so page 601, let's see, 135, that's okay. 7, 9, 11, that's what we just did. Okay. All right, so we'll do 1 through 11. So 1 through 11, odd, and then tomorrow we'll finish the 13 to 19, and then there's a little bit more. Okay, so just 1 through 11 odd for tonight.